this video, we're going to look at Ampere's law, which allows us to find the magnetic field when there's a symmetric situation. And the closest thing to Ampere's law is Gauss's law, which let us find the electric field, in similar symmetric situations. So remember, in Gauss's law, we use the integral around a three-dimensional surface of E, the electric field, dot dA, where dA is like the vector normal to the surface at any point. And in Gauss's law, we said that that integral of E dot dA is always equal to the enclosed charge in the Gaussian surface divided by the permittivity of free space, that epsilon naught. So in Ampere's law, the integral that we're going to use is the integral of B dot dl. And so instead of integrating around a three-dimensional closed surface, we're going to integrate around a closed two-dimensional loop. So now we could just draw a circle on the paper, and that could be a loop. So to illustrate how this works, we're going to look at pretty much the simplest situation that you can have, which is a long straight current-carrying conductor. And the formula for the magnetic field around a long straight conductor, I gave it in my earlier video. It's just mu naught over 2 pi times the current divided by R. So now we're going to derive that with Ampere's law. So the loop that we're going to use is the circular loop centered at the current-carrying conductor. So we have to take the integral around this loop of the magnetic field at every point dot the dl. So at every point on the circle, as you can see here, B and dl are going to be parallel. And so that means we can get rid of the dot product, since they're always 100% parallel to each other. So we can just take the integral around this loop of B times dl. And then at every point on the loop, the magnetic field is going to be the same. And that's because each point on the circular loop is the same distance from this current-carrying conductor. So the magnetic field caused by the wire is always going to be the same at every point on a integration loop. So that means B is constant, and we can move it out of the integral. And we know that if we integrate dl across this loop, then we just get the total length of the loop, which is 2 pi r, the circumference of a loop. And so we find that the integral of B dot dl around this loop is equal to B times 2 pi r. And well, we know what B is because we already have that formula. It's mu naught over 2 pi times I over r. So if we plug this in for B, then you see that the 2 pi r cancels out. So in total, we have mu naught times the current that's going through this loop. So we can generalize this formula. And so Ampere's law says that if we take the integral of B dot dl around a closed loop, then that's going to equal mu naught times the total current, which is inside the loop. Similar to how Gauss's law involved the total charge inside the Gaussian surface. So see here, we have 3 sort of current-carrying wires going through a integration loop, and they're going in different directions. This one is going into the page, and these two are going out of the page towards us. And so you have to pick a positive direction for the current. You can't just add them all up. So to decide which currents are positive or negative, then you're going to use another form of the right-hand rule. So if you curl your fingers in the direction of this integration loop, then your thumb is going to point in the direction of the positive current. So if you integrated around this loop in the counterclockwise direction, then the positive currents are going to be I2 and I3. So to calculate this I enclosed, you're going to do I2 plus I3 minus I1, because this one's going to be negative. So as another example, we're going to find the magnetic field at the center of a solenoid, which is just, wire coiled many times. And so if the solenoid is pretty long, then we can approximate the magnetic field at its center as a uniform field. So it's just uniform and it's going straight horizontal. So the first thing we have to do when using Ampere's law is choose what a closed loop is going to be. So in this case, we're not going to use a circle like we did last time. We're going to use a rectangle. And so you can see the bottom side of the rectangle is inside the center of the solenoid within the magnetic field that we're trying to find. And then the sides of the rectangle are perpendicular to the magnetic field. And the top side of a rectangle, we say that it's very far away from the solenoid, such that there is basically no magnetic field on the top side of this rectangle. So now that we've chosen a closed loop, we just have to calculate the integral of b dot dl around this rectangle. So starting from a to b, b is always parallel to dl at this point, because dl is pointing horizontal to the left, and so is the magnetic field. So again, we can replace the dot product with just b times dl, and then if the magnetic field is uniform, b is the same at every point, so we move it out of the integral, and integrating dl from a to b, we just get capital L, which is this distance from a to b. So that's the integral of b dot dl from a to b. Now we need to calculate it for the other three sides of the rectangle. However, at BC, from B to C and from D to A, the magnetic field is always perpendicular to dl, because dl is going straight up or straight down, while B is going horizontal. So at these points, b dot dl is equal to 0. So we can ignore these two sides of the rectangle. And then from C to D, well, we said that the top of the rectangle is so far away from the solenoid that there is no magnetic field at this point. So of course, b dot dl is going to be equal to 0. So we find that only this bottom side of the rectangle actually matters in the integral of b dot dl. So in total, the integral around the closed path of b dot dl is equal to b times capital L. And so Ampere's law says that this integral, which turns out to be b times capital L, is equal to mu naught times the enclosed current. So now we need to find an expression for the total enclosed current, in this rectangle loop. So in the length L of this, this horizontal distance of the rectangle, if the solenoid has n turns per unit length, then there are n times L turns, in this rectangle. And all these turns carry the same current, I. So the total enclosed current in this loop is going to be the number of turns, n times L, multiplied by I. So replace this expression for the enclosed current, and set that equal to b times L, and we can solve for b. So the magnetic field at the center of a solenoid is equal to mu naught times n, the number of turns per unit length, times the current.